Okay, now let's talk about what's the meaning of bandwidth in electronic communication. In electronic communication, we have a different range of frequencies. Okay, of an electric signal, like electric signal of a voice notes, and electric signal of uh, TV. Okay, they have different frequencies, range of frequencies. So in electric communication, bandwidth is the range of frequencies that an electronic signal uses on a given transmission medium. So what is the range of frequency that any electric signal uses on a given transmission medium? That is the given by bandwidth. So in that bandwidth only, in that range of frequencies only, the resonance circuit will be uh, responding. Otherwise, if it is not comes, if doesn't come under that frequency range, then the resonance circuit won't respond. Like if I talk about the analog television broadcast video signal, then this they have the particular value of bandwidth which is up to 6 megahertz, and this value of bandwidth only the resonance circuit corresponding to this TV will respond. Okay, so there are many electronic circuits, and each electronic there are many electronic signals, and each electronic signals has a width of range, or they have a particular bandwidth for the transmission in a medium. Okay, so bandwidth is expressed in terms of hertz, because the bandwidth is the difference between the upper cut frequency and the lower cut frequency, so it's a measure in terms of hertz. So each signal has a bandwidth. Okay, a voice note has a bandwidth of approximately 3 kilohertz. Okay, within this bandwidth only the corresponding resonance circuit will respond. Okay, therefore it is called decides the selectivity. That means it defines how well a resonance circuit responds to a certain frequency and discriminates against all other frequencies. So that means it will respond to only that value of range of frequencies, and it will discriminate all the other frequencies. Okay, so that's how the bandwidth is used in the communication. Now this calculation of bandwidth is not necessary, the derivation is not necessary, but you have to know the final formula that bandwidth can also be written as in terms of this delta omega, which is bandwidth equals to R by L. Okay, so delta omega is again omega 2 minus omega 1, and omega 2 can be written as, we can this is the angular frequency, we can write in terms of linear frequency also, that is f2 minus f1. In terms of omega 2 we can write f2 minus f1, which is here f1 is omega 1 by 2 pi, and f2 is omega 2 by 2 pi. Okay, in terms of that also you can write. Next is, what is q factor? So q factor is also one of the important term. If you can see here, so bandwidth depends upon R and L. For smaller value of R, the bandwidth, okay, becomes small. Looking at the formula, we can see for smaller value of R, the bandwidth is smaller and the curve is sharp. If the bandwidth is smaller, like this, if this is smaller, obviously this has to be sharp, no? This, if the omega 1 and omega 2, if this is smaller, then this has to be sharp. Okay, and the circuit is more selective. Circuit is more selective in the sense it can only, if this omega 2 and omega 1 becomes smaller, then it becomes very selective, then it can only respond to this small value of range of frequencies. Okay, more is the bandwidth, lesser is the selectivity. If smaller is the bandwidth, then more is the selectivity, and the curve will also become sharp. Therefore, for a smaller value of R, the bandwidth is smaller and the curve is sharp, the circuit is more selective. On the other hand, if the resistance is high, then we can say bandwidth is large and the curve is flat, and the resonance curve is flat. It becomes more flat because if this is more, the bandwidth is more. Understood? So the sharpness of resonance is quantitatively described by a dimensional number known as Q factor. Okay, so Q factor is a quantity which actually defines the sharpness of resonance. Okay, which is called quality factor. Okay, so knowing the quality factor, you can know how sharp the resonance curve is. Okay, so sharpness of a curve is defined by a number, okay, which is dimensionless number, which is called the Q factor. So Q factor is defined as the ratio of resonant frequency divided by bandwidth. Okay, this is the formula for Q factor. No need to derive. Just the ratio of resonant frequency divided by bandwidth. And resonant frequency we know which is omega 0 is given by 1 by square root of LC, and bandwidth is given by R by L. So from there we got the Q factor as this value. So Q factor for LC circuit is given by this formula. Okay, the final formula and definition is this. It's the ratio of resonant frequency divided by bandwidth. So we can see if R is low, C is low, or L is large, then the Q factor will be large. When these two values is low and this value is large, then the Q factor will be large. And the electric circuit with high Q factor values will respond to very narrow range. Q factor is large means the resonance curve is very sharp. Okay, this is called the resonance curve. Okay, whenever I say resonance curve, I'm talking about this. This is called the resonance curve. So whenever the Q factor is large, this is very sharp, and this bandwidth is very small. Okay, the bandwidth is very small. Therefore, when the Q value is very high, then the which will happen when the R and C is very low and L is large, then the Q value should be high, so that it will respond to a very narrow range of frequency because the bandwidth is very less. Therefore, the circuits having larger Q values are more selective. Okay, the value of Q varies from 10 to 100. However, the electronic circuits dealing with very high frequency may have Q even 200. So value of Q can range from 10 to 100, but if you have an electric circuit which has very high frequencies, then the Q value can even go to 200. Okay.